So I'm very happy to sort of being sandwiched in between Peter's lectures, and thank Peter for the invitation to give you a few lectures here. As a guest of the University of Cologne, for which I guess I'm part of the international faculty. In my regular job, I'm teaching at the at Yale University. Actually, I am, as you can still hear from my accent, originally from Germany. I did my undergraduate first in Berlin and then in Frankfurt. And after finishing with, I guess, diploma, it was then called, at the University of Frankfurt, I started my PhD at the University of Pennsylvania and really liked the academic environment in the US and stayed there ever since. I started my academic path at Princeton University, and then after a year moved over to Yale University, where I've been ever since. Okay. What I'm interested in generally is game theory, mechanism design, market design. In my early work, I worked a lot on dynamic mechanisms, learning, Bayesian experimentations, multi-arm bandits, and more recently, closer to market design and information design. And so what we will be talking about here in class is sort of a perfect fit with my own research, and therefore I hope I can give you both a good introduction into the very basic material, but also bring you along to think about what might be interesting question, both at the frontier of research, but also at the frontier of applications. This is of course a great year to study anything like auction. Peter probably told you about the Nobel Prize winners, and in fact, Peter's close association and affiliation with the Nobel Prize winners. Mine is much more distant, but this is clearly a sign that this is both academically very interesting material, but I think more interestingly from the applications it's a very rich set of questions that hasn't by any means seen the end of the day, and new questions are showing up every day. And so this is what I would like to show you today. We will be together today and then again on Monday and then Tuesday. And so in my mind, I have split it up in 6 lectures. So today will be the first 2 lectures. I'll go maybe an hour and 15 minutes, and then I will take a break, and then of 10 minutes, and then return with the second lecture, and we will follow that format also on Monday and on Tuesday. Today I really want to set sort of a little bit the tone, define some of the basic notions that you will have seen in one version or the other already with Peter, but I think it is good to see the core notions in different concepts and in different contexts, and apply them again and again. And then we're going to first think about the revelation principle today, and then as an application, we think about the generalized second price auction, which is basically the auction that drives the a large part of the internet commerce, and particularly all of the digital advertising and the sponsored search design. So it's a huge area. And then in the second part of the lecture, I want to shift gears a little bit, and instead of thinking about private values, independent private values, that's a setting that we're going to begin with today, think about common values and the new economics that appears here. That lecture will, by example, start with my own research, and then we will expand on that a little bit. On Monday, I would like to talk about both revenue and information management. So I'm going to start out with models of price discriminations that are essentially optimal auctions with just one bidder, but a very useful context to think about it. And it then will suggest interesting things about how we can use not only monetary transfers and prices to do allocations, steer allocations, and steer revenue, but how we can also use information to guide consumers' decisions or decisions of economic agents. And so we're going to move in an area that has recently become very popular, very interesting, and very exciting, and that's called information design. and that shares many similarities with mechanism design and market design, but the key object here is information rather than monetary allocative incentives. And finally, on Tuesday, we're going to step beyond static decisions and think about dynamic decisions. Okay, good. And for those of you who just joined, these are the 6 lectures, and I wouldn't mind at all if you were to switch on your audio so that I have a little bit of a sense of the audience. And I also don't mind at all if from time to time you have questions, interrupt me just to slow me down a little bit and also get a sense whether you're following and what are the difficult things and what are the difficult things. Okay, great. And of course, you can also go into chat, and if I miss anything, perhaps Emanuela will tell me and point out to what we should be talking about. Excellent. So the introduction to market design, that's our first topic, is basically going to ask, how can we design a market and a game? We then ask, what are the constraints, what is feasible for that market? Okay. And we're going to formulate and point to 2 important insights and principles, general results, that will help us understanding how we can solve such difficult problems. And the first result that I want to talk about is revelation principle. And by means of example, we will then also think about revenue equivalence among auction formats. And this will be a very important benchmark result, but only benchmark results, as we will see in the second lecture, that revenue equivalence is by no means universal once we think about broader context. And so it's both a benchmark, but also a useful contrast. Okay. You know, market design, mechanism design is in some sense game theory turned upside down, in the sense that when we typically think about the analysis of strategic environments, then we are basically taking the game, the strategic environment, as fixed, and we simply thinking about what are the incentives in these games for the players to behave, and what are the likely equilibrium outcomes that will emerge in that game. So we're taking the rules of the game as fixed and simply pursuing what are the incentives that are being generated by the game, and what are the possibilities for the players to coordinate and compete and lead to outcomes in the games. In market design or mechanism design, we take the opposite approach. So that's what I meant by turning the game upside down. We don't take the rules as given. Rather, we think of designing the rules of the game with a particular objective in mind. And then, of course, we can't just choose the outcomes. It will have to be the case that the rules of the games have to satisfy constraints. These will typically be participation constraints for the players and incentive constraints for the players as well. And within this respect, we then ask, can we achieve what we set out? That's our social objective. It can be a social objective, it can be a private objective. And 2 ways in which we can solve such a problem is by appealing to the revelation principle, and sometimes by appealing to the revenue equivalence result. Okay, so we are taking a very different perspective from what we would if you were to just do equilibrium analysis in a game theoretic setting. But once we define the rule of the games, of course, we need to analyze the game. I want to develop the theory today and then think about the application around one particular example, namely the example of the generalized second price auction. Okay, and the generalized second price auction is an auction format that has evolved somewhat over time and is still evolving. In fact, you will find probably hundreds of people at Google, Facebook, Microsoft, Amazon, Yahoo still working on it and sort of fine tailoring its mechanism. But here's the basic idea. It emerged essentially around the search engine and is often referred to as sponsored search advertising, and has then been applied and is largely adopted in all forms of e-commerce advertising, in particular display advertising, as you see it every time you open up your browser and do anything. It is the main and most important resource, for example, for Google, which makes over 80% of its revenue from the generalized second price auction in either the sponsored search engine or in display advertising. And if you followed a little bit the recent political discussions in the US, I don't mean the election, but I mean the questions of to what extent should we be concerned about market power of digital platforms, then the dominant or allegedly dominant position of Google in the sponsored search is precisely the thrust of the complaint filed by the Department of Justice in its antitrust investigation against Google, and similar things will likely happen with respect to Facebook. Okay, so what's the issue that we are going to try to solve here? Let me give you a little bit of a history so that you have an idea of what's happening. I guess probably the statement here is maybe not quite accurate, but Spectrum auction, maybe in particular, were sort of designed from scratch. Sponsored auctions actually, a sponsored search auction actually evolved in an interesting way over time, and with some interesting misunderstandings of the economic theory, and so that should also tell us something and be informative. So what are we trying to do here is to think about whenever you in your browser, in particular in the search engine, whenever you look for a term. So let's think about pizza in New Haven. That's where I'm currently sitting, and I'm thinking about lunch. New Haven has a large population of Italian immigrants from the turn of the century, late 19th and early 20th century, and there are people who think that the best pizza in America is made in New Haven. So that's what I'm looking for. Emmanuel is probably laughing, or he is laughing. Yes. But I'm giving you information. It's actually quite interesting. So I think New Haven at some point had maybe 60% of its population were Italian immigrants, particularly from the south, so from Sicily and around Napoli, and so that gives added credence to the quality of the pizza, of course. And also to the interesting accent that you can still hear in the stores. Okay, so the problem that we have, whenever you have a search engine, or alternatively, I could think of nicer weather and think about a hotel in San Diego. That would be another item that I could be searching, or I could look for car insurance in Los Angeles. Whenever I put in that search engine, Google is basically allowing advertisers to bid on that search term. And if we were to think about how to price this advertising pre-internet, then the way it would have been done is simply I'm fixing a price for that search term. And then an advertiser, if he wants to list his link or list his display, could pay for it at that fixed posted price that Google would charge. So that's how pre-internet, the New York Times, the Frankfurter Allgemeine Zeitung, all of these journals were doing it. The problem is, of course, that pizza in New Haven, car insurance in Los Angeles, or injury lawyer in Florida, are search terms that carry very different values, both for the person who searches as well as for the potential advertiser, in how valuable it is to establish a contact with the consumer. Okay, and now we all of a sudden essentially have millions and millions, if not billions, of possible search terms that people could be looking for all over the world with all kinds of interest. So how would even a very well-informed company like Google know what is exactly the right price to sell the sponsored search, that is the link that is being shown in the first upper bound to you? Okay. that problem was recognized very early. And so in the early internet advertising starting 1994, what people did was to basically say, well, we're going to price per impression. That is, whenever an impression was shown on the browser, that's what you had to pay for. But still, there were person-to-person negotiating, and there was no targeting of the keyword to the audience, and there was also no personalized pricing to the particular search term. Okay. That changed dramatically in 1997 when a startup, Overture, suggested an interesting version of a first price auction. They basically said, well, you don't have to pay per impression. That is just because your link is being shown in the browser, you don't have to pay. You only pay if indeed the viewer, the user, pays for the click and pays for this particular keyword. And the bids that the advertisers are making for that were going to be completely automated. So it's really a gigantic auction engine that's running behind the search engine, and the bids can be changed at any moment in time. Okay. And then what the generalized first price auction referred to was simply to say, well, once the bids come in, then I'm going to sort the links in a descending order of bids. Presumably the links that are listed higher attract more views. And I'm going to determine as a search engine sort of a cut of how many of the links that I'm going to show as a result of the search engine are going to be sponsored, that is, are going to come from this auction engine, and how many are going to come afterwards from the organic search engine, where the ranking is simply determined by an algorithm that determines the relevance of that link to the search. Okay. So this is how it looked like, and I still remember it in the early days of the internet. So if I put in here the search term car insurance on Yahoo, which at some point was the most popular website to land on, then Yahoo made the decision that is basically going to give you two boxes, two boxes, right? So you see sponsor result here and you see sponsor result here. Those boxes were the links that were being auctioned. And so what you see are names of popular car insurance companies that bid for the link, okay? And at that point, the web designer had simply decided that they're going to have two places, one which is a box at the top of the search engine and another column to the right of the search engine that basically displayed the results from the sponsored searches, from the auctions, and thereafter at the bottom is what I guess they called organic search. And these were results that showed up not because the bids were high, but because the algorithm that Google ran or any other search company ran determined that these were the links that were likely to provide the most information and were likely to be the ones that the audience might click on. Okay. So this is how it looked like. Okay. And in fact, an interesting part of the design of the search engine at that point was that Yahoo had decided that it's going to actually disclose quite a bit about how the ranking in the sponsored search engine came about and what the price was that the advertisers paid, that is the maximum bid that they submitted, so that one could both get a sense on the prices as they were established on the market, but also the competitors had an idea how much they would need to bid in order to meet or exceed the currently prevailing bid by a competitor. Okay, so what you can see here is that each advertiser basically submitted a maximum bid. This bid can be adjusted at any moment in time. And as you notice, these bids were ranked according to the price. And so Geico, which had the highest bid, $10.49, got ranked number 1. Progressive, which had the second highest bid, $10.48, got ranked 2nd, and so on. Okay. As an interesting part of the history, then, this information was initially available, but as we moved on and forward or come closer to the past, the design of the market for search engines and display advertising changed to become more opaque, and nowadays the advertisers have less common information. They often get price recommendation and bid recommendation, but these are information that are basically fed by the search engine and will of course some relation to the market prices, but much less transparent. Okay.
Can I ask one question?
Yes.
It's surprising that the bids are only 1 cent apart, 1 and 2 and 3, 4.
Yeah.
Okay. So it seems that I should be willing to pay like an extra cent to be the first rather than the second or something like that. So is there an equilibrium?
So remember, I mentioned it, that in the beginning, this was designed as a generalized first price auction. That means I'm simply ranking it according to price, and then I have the person who makes the highest bid ranked number 1, and he pays his bid if he's being clicked on. The second highest bid gets a second rank, and he pays his bid if he's clicked on. Okay. These bids indeed could be changed at any time. Okay. And so you can see how this is both a snapshot of the market at the current moment, where it just so happened that Geico outbid Progressive by bidding 1 cent more. But as you suggest, Emanuele, this is unlikely to be an equilibrium or a stable outcome of this game, because if it's the case that there's a big difference between the first and the second position in terms of the likelihood of attracting the viewer, then once Progressive has seen that the $10.48 are not sufficient anymore, it might easily update its bid to go to $10.50. And so what we're seeing here is probably an instance where Geico has just jumped up in its bid to beat out Progressive, and it, for a moment, for an instant, for a minute, for an hour, it's ahead. But the next time Progressive is going to think about adjusting its bid, and of course this is now run all by algorithm, it is probably going to jump ahead. Okay. Actually, if you go down one more level, right, so you see something similar happening here. Thank you for pointing this out. E-insurance and State Farm are also tied very closely to each other, and we expect there may be some rearrangements also about to happen. Now it's right, because just 1 cent more will State Farm, or 2 cents more will give State Farm a jump up in its ranking, but that's sort of the local competition. If you think about moving up to be number 2, then e-insurance has to think pretty hard whether it really wants to go from a bid of $9 to a bid of $10.50, which essentially it will have to do. Okay. So that's an excellent point. And in fact, that was a problem. And in fact, this design turned out to be eventually abandoned, because as we just observed, the outcome of the first price auction is inherently unstable. And in fact, one can show that if I was going to try in this multi-position, multi-ranking auctions, going to try to compute an equilibrium, there is no pure strategy equilibrium. There will be only a mixed strategy equilibrium. In this dynamic that is auction that develops over time, what that means is that the strategies of the bidders are basically requiring permanent adjustment and scope for a better response of the bidders to just barely outbid my competitor. And it's therefore a design, an auction that requires a lot of attention from the advertisers, that requires a lot of strategic reasoning, that would give them scope for investing in, better algorithm, faster response times, and all of these things, which are in some sense orthogonal, that is should not be the concerns of the advertiser. What they should think about is which are the consumers, which are viewers that they would like to reach, and how do they reach them, and what's the best way to provide information and then value to them. They should not have to think about the dynamic bidding strategies. Okay, and so let's do a little economics, or let's do a little numbers, right? So think about the following example that I want to focus you on now. So think about, we're having two slots. That is, the search engine decided that it wants to allocate 2 slots in the sponsored search, and afterwards it's going to display the organic search. Suppose we have 3 bidders. The first slot gives us 100 clicks per hour, just to have some numbers, and the second slot gives us also quite a few clicks, but just 70. Okay, and then the bidders there are 3 bidders, 1, 2, 3. They have values per click. That is $10, $8, and $5 respectively. Okay. Okay. So now, relative to sort of the single unit auction that you might have seen in the early lectures of Peter, we have a little bit more of a complicated allocation problem here, because we essentially have 2 units that we have to sell, namely slot 1 and slot 2. And the units are not the same. The first slot is inherently more valuable than the second slot. Okay. Still, we are basically trying to solve this 2-dimensional allocation problem, since we have 2 slots, by means just of a single-dimensional bid. And then we're going to use a single-dimensional bid, namely what each bidder is going to bid, by simply sorting and allocating 1 slot to bidder 1 and 1 slot to bidder 2, or bidder 3. Okay, good. So the simple observation is, in this example, we don't have a pure strategy equilibrium of the game, and it's easy to convince you that, right? So and in fact, why don't we well, let's try to construct an equilibrium and see what's happening. Okay. The third bidder is the weakest one. He only bids at most $5. That's his value to be in the slot, okay, per click. So that's what he's going to bid. The second bidder is sort of a strong bidder, but not quite as strong as bidder 2. So inductively, we say, well, he should bid something above $5, but there's no need to bid very much more than that. Okay. And so let's say he bids $5.50, then bidder 1, of course, is going to drop his bid eventually, think about this sort of evolving over time, to something just above $5.50, because that will be enough for him to get into that slot. So think about $5.75 or something. And this would give us sort of the right sorting, in some sense, of the bidders with the highest valuation will get the most valuable slots. But of course, just with these arbitrary numbers, $5, $5.50, $5.75, now all of a sudden bidder 2 is going to recognize, I can get actually the better slot that gets more clicks per hour by just increasing my bid a little bit, and therefore I have a higher quality object, and I'm going to go up. And so now you see how we're basically racing up towards $8 for slot 1. And once we're there, of course, bidder 2 says, well, I'm going to not be able to eventually outbid bidder 1, so I'm going to focus on the second slot. But in order to get the second slot, I don't have to bid $8. I just have to outbid the third bidder, which is somewhere going to be around 5. So now he's going to march down. Bidder 1 is following him, and so we basically have this oscillating dynamic in the bids that clearly will not be a good dynamics. It will be just too much volatility for not much. And so the big insight of a group of actually economists at Google was to say, well, why don't we switch it from a first price auction or a generalized first price auction, where the generalized simply refers to the fact that we have more than one object. Why don't we switch to the second price auction, where there's much less strategic reasoning and gaming necessary, okay? And the interesting way is that the way they understood, it was actually not Google, but a company that was eventually bought by Google, the way they understood the second price auction, or the way to generalize it, was to say, well, if we have one object, what we're going to do is we're going to sort all the bits in increasing or in decreasing order, and then the person with the highest bid gets the object, but he only has to pay the second highest price. What's the generalization that we're going to offer? It's going to say, well, since we have many slots to offer, we're going to say the highest bid gets the highest slot and pays the second highest price. The second highest bid gets the second highest slot and pays the third highest price. Okay, it seems like a very natural generalization, and we're going to see later on that this is just one of many possible generalizations of the second price auction, actually one that would not have been suggested if one had started with the classic results of Vickery, Clarks, and Groves, which we're going to talk about, but rather something else. But nonetheless, that's the auction they suggest that they implemented on the search engine, and later others followed. And this is the auction, at least to the extent that we can, sort of see and pursue it today, that it's being run by Google. Okay, so here's some nice material from Google's website. They don't say quite that much, but that was what we're saying then. Google's unique auction model uses Nobel Prize winning economic theory to eliminate that feeling that you have paid too much. Okay? And by Nobel Prize winning economic theory, they then referred to the Nobel Prize that Vickers had gotten for the Vickery, not Vickers, another famous English economist, Vickery had gotten for the second prize auction, Vickery. Okay. Okay, but it turns out that the Vickery auction, we're going to think about this for a second, is actually the second prize auction. The VCG mechanism that would be suggested is quite different when we have multiple slots. Okay, and I'm seeing here that I have some problem. Good. Okay, so with just one slot, indeed, the generalized second prize auction that I just talked about is identical to the standard second prize auction. With multiple slots, however, there's going to be a distinction. In the generalized second prize auction, or GSP for short, the bidder K, the K's highest bidders, pays the bid of K, K plus 1, the Vickery, Clark, Groves mechanism. So that's the acronym that we're going to use to refer to this body of literature that really defined the notion of an efficient mechanism. What bid is charged? He's being charged for the externality that he imposes on all the other bidders, and that's potentially something quite different. So there's an interesting misunderstanding of theory that's even evident in the marketing material, and today we're going to think a little bit about where this misunderstanding is coming from, and try to relate and explain some of the differences from a general theoretical perspective, and then bring it back to the practice. Okay. Excellent. Good. So here's a great moment for me to pause to be sure that all of you sort of have a view now of the auction that is essentially running behind all of the search engines, and that in real time, minute by minute, second by second, is determining the prices and the allocations that you see whenever you enter a search term into a search engine. Okay, so we're going from auctions that have been performed regularly in the auction houses for art, Sotheby's and the like, which meet in the spring and the fall under nice conditions in New York, London, Hong Kong, and all over the world, for a set of rather exclusive bidder, to an auction that is running second by second, open to the entire world, and essentially selling of millions and billions of search terms at every second. Okay, so this is, if you think about scale, size, volume, all of these things, it's just a gigantic leap. And so, of course, when we think about auction theory today, we want to address both concerns, but you can easily imagine that running an auction at the scale of Google size or Facebook size is something quite different than running an auction at Sotheby's. And so a lot of interesting things that happen at that intersection between economics, computer science, operations research, data science, that basically brings together economic insights and then issues of scale, issues of complexity, issues of computational ease. Okay. And the final thing that I'm going to say is that I really don't mind at all to have your video on and asking me questions, so that we have a little bit of interaction. It's just monotonous dialogue of me talking. Okay, though I clearly have enough material to get us through this lecture. Yeah. And so, as a substitute, Emanuela, I also don't mind if you ask questions, just to give me a break and allow me to have a sip of coffee. Wonderful, good. So this is the example I want to think about today. The generalized second price auction. Maybe think a little bit about the generalized first price auction. I want to think about this as particular instances of auctions. But of course, I can think about many other ways in which I could sell off these items. I could solve this allocation problem. We mentioned posted price. We mentioned the variation from pay per click, pay per impression. We mentioned one could also change the sizes of the links and sort of have people pay more for bigger advertising, less for smaller advertising. I could just try to clear the market by posted prices. So there's basically an endless variety of possibilities that I could think about. And now we want to set out a framework in which we can think about what's the best way to solve this problem, and what is a way in which we can manage the solution to this almost infinite variety of possible designs that we could offer. Okay, and that will bring us to the revelation principle, and that will bring us to a definition of what is a Vickrey-Clark-Groves mechanism. Okay, good. So for this, we need a little bit of a formal language. We need a little bit of notation to formulate what is the environment that we're thinking about. We want to think about a finite number, but remember the internet. This can be a large number, okay, a finite number of agents. Each one of the agents has some private information. Typically, that will refer to his willingness to pay for that object. So you can think about this being the advertiser who is willing to place his advertising on the search engine. We're going to typically adopt a Bayesian point of view. That is, there's going to be some common prior distribution over the private information, the theta, which encodes some information that the bidder has. We will often ask whether we can find a solution concept that does not require the exact knowledge of the common prior distribution. So that is prior free or detail free, as Wilson would say. We want to think about the allocation as, in general, having some monetary dimension. So that's the price that I have to pay to guarantee myself something as a bidder, T1 to Ti, and some non-monetary dimension, that's the allocation, that is, for example, the rank that I get in the search engine. Okay. these two elements, the allocation and the transfer, will determine the utility of a bidder. And so that is going to be the last term on the slide. That simply is going to think about the net utility, UI, is going to be the value, the gross value of getting a particular allocation X. Okay, so this is the gross value, and then we're going to subtract from it a payment, so that UI is what we call the net utility, or the indirect utility that I'm getting from the allocation Y, that combines both the allocation as well as the monetary transfer. Okay. And we will, in this lecture, think about largely quasi-linear preferences. That means that we're going to have a distinction between this term, which has an arbitrary interaction between the allocation and my private information, the theta I, but then there is a linear term here at Ti, and so that is the quasi-linear formulation that we are adopting. Okay. Another way to say this to the economist is there's basically no income effects here. Money just directly and linearly translates our utility. Okay. When we think about mechanism design, what we want to solve is essentially the following problem, and this commuting diagram, which you see in the center here, is really something to visualize and to keep in mind. Okay, so we want to think that the objective that we have in mind, and so here I come back to my initial opening words, we have an objective that is this function f here, the social choice function, that says ideally to every profile of preferences, and ideally meaning if we could access this private information, we would like to suggest a function f that maps every profile of preferences into a particular allocation y. Okay, so that is the upper line. That is what we would like to achieve. But we are aware of the fact that this part here is the private information, and we're going to try to elicit that in private information by getting some message, some information from the agents about that private information. Okay, that is, we're going to offer them a language in which they can express their information, and we're going to, as part of the mechanism design, choose an outcome function that is G here. Okay, that is a promise of mapping the information, the messages that were M for messages that we got, into an outcome Y. Okay, so the mechanism design is, or the market design is, how to choose the message space. That is, what are we allowing them to tell us, or what are we willing to process as information, and then how we're mapping that into an allocation Y. Okay. This is what the market design needs to choose. So these are the rules of the game that we are defining. And once we have defined those rules of the game, then the participants, the agents, can think about a strategy by which they translate the information they have privately to them, and communicating to us, well knowing that that communication is then going to lead to a set of decisions by the designer, by the seller, by the principal, by the platform, if you wish, that will give them a final allocation. Okay. So there's the first prize, there's the second prize, there's in English, there's a Dutch auction. All are these are variants of this market and auction design. And when I talk to you about the large variety of mechanisms, then I just want to point out that M, the set of messages that I'm going to allow, can be very large, and so can be the outcome function G that maps the messages into the final outcomes. Okay. Why? Because I can think about many ways in which I'm going to collect that information. Okay, I can go back and forth between the bidders and ask them some initial information, as I'm going to do in the ascending auction. Then I'm going to ask them some more information. Then I'm going to ask them some more information. I can also do bilateral communication, then basically move from one bidder to the other and tell them, well, bidder one told me he's willing to pay that much. How much are you willing to pay? So you can see there are a lot of negotiation settings, communication settings that I can choose, that all in the end of the day are going to be leading to a complicated mapping from the messages into a final outcome. If I think about this now sort of as a choice space, as an optimization space for the designer, it's going to be a huge space, and it's going to be very hard to find the optimal solution. Okay, and in fact, it's almost unrestricted in how complicated I can make the back and forth in terms of collecting the information. Okay. So we need to get a handle on this a little bit. And then we also need to acknowledge that, of course, the agents will have their own interests. They want to maximize their own utility in this game. And so whenever we offer them an outcome function, in some sense, whenever we offer them a game, they will choose their strategies so as to maximize the utility. So that's something that, from the point of view of the designer, we have to think about as a constraint. Okay. And so here are the main constraints that we're going to think about. We're going to think about incentive constraints, and we're going to think about participation constraints. Incentive constraints are going to refer to the fact that the agents are going to tell us the right bit of information. Okay, so let me go slow here. Right, we're going to now think about one specific mechanism, and in fact, it's one that I'm going to refer to as direct mechanism, because I'm going to say, well, let me pretend that I want to implement the social choice function, and let me suggest that the messages that I would like the agents to convey to me are simply going to be their true preferences, their true types theta I. Okay. And what I would like to say is, what I would like to accomplish is that whenever, so this is the indirect utility function, whenever an agent is of type theta I, he's actually communicating to me precisely the same type theta I. And I think, great, okay. My apologies. Excellent. So, so we were at the incentive compatibility. Okay, so we want to say it is better for the agent to tell me the truth, that is, report me the true type, rather than misreporting. Okay, right? And so if you look at this inequality, what you want to say is it is better when my true type is theta I to report the type rather than report anything else. Okay, and we're going to say that this incentive compatibility is a dominant strategy whenever telling the true preferences is a good strategy in terms of the inequality, irrespective of what the other strategies are. So this is the qualifier here at the end, okay? The symbol, the upside down A, is basically the universal qualifier for all possible reports that are going to come in from the other players, and minus I simply refers to all of the other players. Okay. And then the second constraint that we typically want to respect is the exposed individual rationality constraint, which is simply to saying the net utility that I'm getting from the allocation, that is the value minus the price that I have to pay for it, must exceed the value of my outside option. So that means that I'm willing to participate in this mechanism. Okay, so incentive constraint and participation constraint are the constraints that we're going to impose that the mechanism needs to satisfy. And once we do that, then there are still many ways to elicit information, many language, many procedures, many queries. Okay, the question is there may be a canonical and a universal mechanism, and that is precisely the famous result that was proven in many versions in the 70s and early 80s, and has been referred to as a revelation mechanism. Okay? And so what does it say? Well, it says that whenever we find a mechanism that allows us to implement, that is to realize a particular social choice function, then we can find another mechanism, and in fact a direct mechanism, where all that we're going to do is to ask the players to directly communicate to us their preferences, and where we're going to choose as an outcome function simply our original social choice function. And in fact, we will be able to do that in a way so that telling the truth, that is reporting from the player's point of view precisely their preference, is a dominant strategy equilibrium. So DSE refers to simply the acronym of dominant strategy equilibrium. Okay. So the full statement of the theorem is that for every mechanism gamma prime, that could be any arbitrary procedure M prime and G prime, and if there is a pure strategy in this mechanism, then there does exist another mechanism that is direct, that is simply asking them for their preferences, asking it just once, and allows the social choice function F to be implemented directly as the outcome function, such that one, every player tells the truth, so sigma I is simply going to be always be simply telling the truth, and B, what we're realizing is precisely the outcome that we started with, the G prime and the equilibrium theta prime, and it gives us precisely our social choice function. Okay, so this is.
If I may interrupt for with a quick comment, and that is there's two extensions here that Dirk's focusing on that further illustrate the power of mechanism design. We focused in my classes on interim incentive compatibility and interim individual rationality. And as you can see, what Dirk has here is dominant strategy incentive compatibility and ex post individual rationality, both of which are stronger. And so he's imposing a strengthening of the constraints that the mechanism designer has to work with, and yet he's still able to get very powerful results. So that's, I just wanted to make that connection.
That's wonderful. Yes, thank you, Peter. Okay, and that strengthening is going to be possible in many settings, but is by no means a universal property of mechanism design. And so that's something that we will have to keep in mind. In particular, we will come back to in the second lecture. We see that insisting on a stronger version of incentive constraints and participation constraint, as we do here, will sometimes come at a loss, and will mean that we will be able to achieve less, either in terms of the social objective or in terms of the revenue objective. But in some, and in fact in sort of many canonical settings, there is going to be an equivalence. That's some of the work that actually our colleagues in Bonn have worked on for a long time, in particular Benny Moldovano. So this is a very interesting set of questions. Okay, good. So we are taking for granted now that we can use the revelation principle. We're going to take as constraints these relatively to the interim constraint strong ex post constraint. So that's a useful language that we will often refer. Ex ante means that we're evaluating our utility before we know anything about the realizations of the type. So we're just basically forming a full expectation. Ex interim will mean that we are evaluating our choices, knowing our own type, but not yet knowing the types of the others. And ex post or dominant strategy will mean that I can count on knowing not only my own type, but I'm even considering either the reported or the true types of the other players. Okay? So ex ante, ex interim, ex post are basically sort of different moments in the games, and they refer to different pieces of information that I have when evaluating my choices. Okay. So let's start out by thinking about what would be the socially efficient allocation now in this general setting that I gave to you, okay, in terms of the utilities of the bidders and their preferences, okay? And then in the second lecture, we will think about individual objectives, then we will think about revenue maximization. And here is a set of results that was proven in increasing generality by Vickery, Clark, and Groves. Actually, Vickery's 1961 article is still wonderful to read. And often the classics, that is the original papers, are so much nicer in their intent and straightforwardness than the textbook description. So I always encourage you to do that. So what we want to think about when we think about socially efficient allocation is to think about maximizing the social surplus, that is the sum over the gross utility of all agents. So this is this expression at the bottom here. Okay. That is, we want to find the allocation that maximizes the gross utility. And for the moment, we are not yet thinking about the transfers, because the transfers we're simply going to use to shift the utility back and forth between the bidders and possibly the sellers. But from a welfare point of view, they're neutral. They simply cancel out. So all we're thinking about here is to find that allocation that maximizes the sum of the utility of the agents. Okay. Good. And Vickery, Clark, and Groves basically suggested that a very simple, or the following mechanism, the following transfer would allow us to achieve the socially efficient allocation in an incentive compatible way. Not only that, in an incentive compatible and dominant strategy way. Okay. So what we're suggesting is we are now going to provide incentives to the agents to report their type truthfully. And how are we going to do that? Remember, our objective is to maximize social welfare. Okay. And so what we're going to try to do is to make every individual, when he has to report his private information, to think as if he were going to maximize the social welfare. Now, a priori, that's not his objective, because he has just some private utility function. But what we have left unspecified and what we're going to use now is the fact that the transfer function can actually depend just not only on my own report, theta I, but on the report of all the other agents. And by choosing that function in an appropriate way, it is as if I can reconfigure the gross utilities into net utilities of the bidders, so that he behaves as if, in fact, he wants to think about the entire community. Okay, so the transfer that the agent I is supposed to pay does depend not only on his own type, that's a theta I, but it depends on the entire type profile, the vector of preferences, theta, okay? And for the moment, we allow that theta to not necessarily refer to the true types, but to any arbitrary type. And we think, well, whatever those types are, however this report's going to come in, you will have to pay us just the negative of what the value is that the other agents were getting if we're trying to maximize the social welfare, that is the F star, under the reports that came in. Okay, so that transfer function simply pretends that the reports are the true reports, are the true preferences, and then computes the externality that agent I imposes on all of the other agents. So we're summing up over the utility. So that's the second point that we should observe here. We're thinking about the utilities of all the other agents, all the agents other than I, right? And we have the negative of it. So if you think putting it together, the utility VI plus the monetary transfer, then altogether it is as if every individual agent is maximizing the social welfare. Okay, and the result that we therefore get is really a Nobel Prize winning result. Namely, every efficient social choice function can be truthfully implemented in a dominant strategy equilibrium by a VCG mechanism, by a Vickrey-Clark-Ropes mechanism that is going to be a direct mechanism that's going to take as input simply the allocation that maximizes social welfare. Okay. Yes. Right. So now notice that actually we did not dwell at all very long on what is the allocation space X. We didn't dwell at all on what is the problem that we want to solve. So this is really a general allocation problem that goes way beyond a single unit, a multi-unit problem. This is something that can solve, for example, public good problems, where we're thinking about, should we install a bridge that goes over the Rhine? Should we build a new opera house? Should we build a new theater? Should we build new schools? These are all decisions that depend on the evaluations of the citizens, and for which we would like to know what their assessment is to then make the socially efficient decision. Okay. Okay. But of course, it tells us also something about what we should do in the second prize auction. Okay. So think about now just having a single good. Okay. And thinking about what should an agent I pay, okay, that will also come tell us that the second prize auction will actually allow us to implement a socially efficient good. Okay. Good. What we did so far, okay, when we specified the first term of the social choice function, and that was basically this term here. Okay, sorry. Let me just remove this for 1 second. Okay. Oh, I'm taking the I. Okay. We basically just looked at the second term. Okay. That term made it such that the individual thinks in terms of the social welfare. Okay, we can add constant to this transfer, and that will basically allow us to not only guarantee the incentive compatibility, but also the individual participation constraint. Okay, so I'm now suggesting one very specific transfer payment that's often referred to as a pivot mechanism, that exactly represents the social externality cost. So to this second part here that we started out with, we are now going to add this first part that looks very similar, okay, but evaluates the utility of the agents not at the social welfare maximizing allocation when all agents are present, but at the social welfare when we're going to remove agent I and simply think about what we would do in the absence of agent I. Okay. And so now we basically have an expression that tells us that's precisely the externality cost that agent I is imposing to society. In the presence of agent I, we're going to pursue this. Okay. But in the absence of agent I, we would pursue this. Okay. What agent I therefore has to pay in order to get, in some sense, his influence and his pivot being counted is just the difference between what we would do without him and what we would do with him. Okay. I mentioned before that should hopefully give us the second price auction back if you're interested in allocating just a single good. Okay. Why? And it does indeed, in fact. Okay. Why? Because what are we going to do if agent I, who we may think of allocating the object to, were not in our game? So this is this first term that we're going to look at. Well, we would give it to that person other than I who has the highest value. Okay. And so the payment that he has to make is essentially what is the next highest value in society. Okay. And of course, if he's present, we're going to give it to him. And therefore, the gross utility that the other agent's getting is equal to 0. Okay. So this term in the second price auction is going to be equal to 0. And this is simply going to be what we often call as the second highest valuation. Okay. And that's what he has to pay. Okay. Another way to put it is that in equilibrium, in the indirect utility, what does agent I get? Well, he gets his marginal contribution, which is his utility minus the externality cost, right? So now we're going to say, well, in his presence, we're going to maximize over all of the agents and all of their information. In the absence, we would simply find the solution that's best for the remaining. Okay. The marginal contribution to society, to welfare that agent I has is precisely that difference. Okay. And what we're going to try in equilibrium to achieve is that in terms of the net utility, okay, he's getting precisely that. And of course, for the winning bidder, the net utility comes about by getting the object while he has the highest willingness to pay and paying the second highest utility. And so we are back at the second price auction. Yes? Okay. Right. So what we have seen now is that there's a general way in which we can achieve an efficient outcome for a general allocation problem. We refer to that as the Vickrey-Clark-Groves mechanism. That can be done in a direct mechanism. That was the revelation principle. And in fact, in this environment here, the equilibrium notion that we can choose to work with is the one of dominant strategy. So a very strong solution concept that doesn't take into account the prior distribution. Okay. Okay, so now I should maybe have emphasized this a little bit more. The reason this works so nicely is for two sources. One is that we looked at what we call private value setting. That means that the utility of bidder J is only dependent on the allocation, of course, and his own type. So the value for bidder J is just determined by his own type. That's what we're going to think about as private value. Okay. We're going to talk later today about common values or interdependent values where that's not the case anymore. And then we won't have such a strong result. And second, the objective function that we chose, namely maximizing of the socially efficient allocation, that objective function F star could be formulated realization by realization of the preference profile. So it did not refer to an expectation that is formed on the basis of the prior. And so because the social objective is profile by profile, and because we have private values, we have such a strong result as being suggested by the BCG mechanism. Okay. Okay, so we have a general solution, we have a general equilibrium notion, dominant strategy, and we have a general efficiency result that is supported by this insight of the revelation principle, namely that we, without loss of generality, can focus on direct and truth-telling mechanisms. That's the main theoretical insight of this lecture. And now we're quickly returning back to our GSP generalized second price auction and think about what this insight of the Vickrey-Clark-Groves mechanism tells us in this many unit allocation problem. Okay. Yeah. So stay with me for the last 5 minutes, in which we're going to 5, 6, 7 minutes, in which we're going to now see what the implications of the BCG mechanisms are in the specific context of sponsored search. Okay. I remind you, we have 2 slots, we have 3 bidders. The bidders have values that are ranked by $10, $8, and $5 per click. Okay. We saw that under the general second price auction, we are basically going to drop the prices down to $5 because that is just the price at which the third and the second highest bidder are indifferent. Okay, and we're going to drop the price of the second of the highest bidder down to $8 because that's the price where he's just indifferent. And then we can verify that is once we multiply this by the number of clicks per hours, that the payment that we're going to get are going to be 800 and 350. Okay. Okay. Now, I skipped over something here. I tried to slide something under the rug, because what did I do? I pretended here that somehow in the second price auction, in the generalized second price auctions, the bidders tell their valuation truthfully. That is, I'm assumed that the highest bidder bids $10. He has to pay the second highest bid. I assume that the second bidder paid $8 or made a bid of $8. Of course, he doesn't have to pay that. He has only to pay $5. And I pretended that that is going to be the equilibrium bid under the generalized second price auction. And therefore, that's the basis on which we can collect the revenue for the search engine. Okay. And we're going to hopefully realize in a minute that that was sadly just pretension. That is, these bidders will find better ways to bid in the generalized second price auction that will not lead us those high revenues. Okay. Okay. What would the VCG mechanism suggest? What would the externality suggest? Okay. Well, the externality mechanism would suggest that, or the analysis through the externality would suggest that by displacing bidder 3, right, bidder 2 basically takes away a value of $5 per click multiplied by the number of clicks 70, takes away a value of $350 that we would otherwise generate with bidder 3. So that's what you would pay. Okay. Now, what is, so in fact, that's exactly what should happen. Okay. Now, what does bidder 1 have to pay? Okay. Bidder 1, okay, by being present, of course, also takes away the possibility from bidder 3 to getting the second slot, because he's basically pressing down bidder 2 to a second slot. Okay, he's pushing him down, so therefore he's pushing bidder 3 out of the auction. So he's also going to take away the $350 from bidder 3, but he's also pushing bidder 2 down from the first position to the second position. Okay, and with that comes a loss of 30 additional clicks. Okay. And they are being valued by $8 by the second bidder. So 8 times 30 gives us another $250. So if we were to think and take the VCG mechanism seriously, what we would think is that the payment that the first bidder would have to do is the sum over these 350 and the 240. Okay. So that is the calculation that would follow from the Vickrey-Clark-Grove mechanism, right? Good. But let's first notice that actually truth telling is not a dominant strategy under the generalized second price auction, right? Because you know, bidder 1 is realizing, well, if I have to pay $8 to get at the first position, a better thing for me to do, that's a very high price. Okay. And what I'm left over is just a net value of $200, namely the difference between my value and the price, times the number of clicks. A much better thing to do is to not bid as aggressively get just a second slot. That means I'm going to get a little bit less in quantity, but I also have to pay a lesser price. And the resolving net utility 10 minus 5 times the number of slots would give me a higher net utility 350. So we have basically shown that this can't possibly be in equilibrium under the generalized second price auction. Well, the generalized second price auction is also not a direct mechanism, it's an indirect mechanism. It tries to get to the values in an indirect way. So it's an example of an alternative mechanism. And what we want to do is to see whether we cannot establish a closer relationship between that indirect mechanism and the direct mechanism. Okay. The first observation we now made is that actually our pretend solution cannot be a solution for the generalized second price auction because it's not an equilibrium. Okay. Well, let me see whether I want to give you the equilibrium. Well, it's right. Right. So what will happen here is that in the general second price auction, bidder 2, of course, doesn't have to bid $8. He can bid less and still get the auction. So he will do that because he doesn't want to pay that much. Okay. So he can lower his bid. And when he lowers his bid, bidder 1 can also lower the bid. And so the equilibrium of this game will in fact be one where the revenues are lowered, but they will turn out to be exactly equivalent to the VCG mechanism. And that, in fact, I will leave you as an exercise, and that will be the first exercise that you will see from me. Okay. The material that we referred to here, that we used here as background, are 2 articles that really set the stage to think about the internet position auction, as there's something called. One is a paper by Edelman, Ostrowski, and Schwartz. That's in the AER, and I will give you the reference. And the second paper is a paper by Halvarian, who still is the chief economist of Google, who called these the position auctions. These papers were written roughly at the same time, but since one was used for Google internal purposes, it came out much later. But these are really classic papers. The math behind them is quite straightforward, elementary. So again, I would strongly recommend you to have a look at these 2 papers. Good. I think this is an excellent moment to take a little break, to take a little pause. If there are any questions, I'm happy, of course, to take them. But otherwise, I would say, why don't we take a little break? It's 12:20 now here, so that means it is 5:20 in Cologne. I actually forgot to say that I grew up in Bonn, and Bad Honnef actually, so very close to Cologne. And I just realized that the last time I was actually visiting Köln in person, it was maybe more than 20 years ago when I was buying the outfit for my wedding that was happening a few days later. And so I have very fond memories of walking through Köln and making nice choices together with my future wife. So hopefully I'll be able to join you in the next terms in person. But for now, this is how we're going to communicate. Let's take a break here and let's meet in 10 minutes. So are you Emanuele as well?
I am, thank you.
Good. Okay, great. So you have access to a set of slides that basically covers all of these 6 lectures. The first lecture was on the Vickery-Groves-Clark mechanism and the generalized second price auction. Contains a few additional slides that you should feel free to study at your own time and at your own leisure. We're now going to move to a contrasting setting and with sort of new insights, new challenges, new problems. One in which the value is not private, but rather is what we often refer to the auction world as a common value model. And second, what we're interesting now is not attaining the socially efficient outcome, but rather attaining a private objective, namely maximizing the revenue for the seller. Okay, so the environment is going to be now simpler, as we're going to focus just on the single unit allocation problem. We just want to sell off one object, but that object has a common value. That is, it is the same for all of the bidders, except what distinguishes them is that initially they only have some private noisy information about what the value of the object is. And so their bidding is going to be informed by that private information. But in the process of bidding and in the process of allocating the object, from the fact that they're ranked high or they're ranked low in the bids, they will get additional information that will allow them to update what the true value of the object is. Okay, and at the very extreme of these two settings, where on the one hand side, all I need to know for the valuation of the object is my own information, to the value of the object is simply determined by all of our values, which is a common value, is an entire spectrum that we refer to of interdependent values. That is also interesting to study. Today, we're going to focus, just as we started out at one extreme, which is private value, we're going to end up at the other extreme, which is the common value setting. Okay. The setting that we're going to focus on today is a little bit less general. And in fact, it draws very much from a paper that I wrote just this last year with Ben Brooks and Stephen Morris. These are the co-authors. And so the paper with the same title, namely Countering the Winner's Curse, Auction Design in a Common Value Model, is sort of the background reading for this class. We were fortunate, though, in developing this model and this results to really use some very beautiful canonical and foundational insights from Jeremy Bülow and Paul Klemperer that I will cite as we go through, so that even though this is research from this year or last year, the insights can be formulated in a way that is completely and entirely accessible to you as masters or graduate students, PhD students. Okay, and in fact, is probably excellent material for some kind of textbook treatment at some point. Okay. Good. So with that as background, the new element that's going to come into play now is the interdependence in the values, and resulting from that, a new phenomenon that's key in many markets, which is the winner's curse. And so we will have time to talk about these two things. Okay. With interdependence in values among the bidders is frequent in auction and frequent in auction problems, right? There is a the ideal private value setting is one where really our value for an object is driven entirely by our idiosyncratic taste, and just because I like a painting, it doesn't mean that Emanuele will have the same taste, or Peter, and so in fact I couldn't care less about what their estimation and what their connoisseurship is about these paintings. I have my own private subjective taste that alone determines my value. By contrast, in many markets, think about in particular in financial markets where I'm owning an asset, clearly the value of the asset is going to be the market price, and that's going to be determined not just by my own opinion, that would be a fortunate coincidence, but by the opinions of many other financial traders. So think about we're bidding for a natural resource such as an oil tract that we can explore. I will have information about that oil track, but my competitors, the other drilling companies, will have some information too. If we think about investment banks competing for selling shares in the initial public offering, the investment banks will have some view on how much value the company has, the new company, the startup. But other investment banks will have diverging, different, concurring opinions that will all be part of forming the prices. Okay. Lenders competing in syndicated loan markets. So a big corporation often asks for loans from banks. The banks loan, individual banks don't want to grant, but together in a syndicate, they're willing to grant. Again, what is the credit risk here is something that individual banks have some idea, but the joint opinion of the bank is what eventually will determine the value at which this is going to be offered. Okay. The winner's curse that we're going to refer to is the fact that winning or losing the object is now going to be informative about the value estimates of the competing bidders. Okay. And so if I'm in an auction, I must account for that in my bidding behavior, because I'm going to realize that after I submit my bid and after I'm being informed about whether that bid makes me a winner or loser, in fact, that additional information will tell me something about the other bidders. If I'm a winner, it meant that all of the other bidders submitted a bid that is below mine, and therefore their opinion about that asset is probably less positive than mine. Conversely, if I'm a loser, I'll find out that my estimate was probably a little bit too low and I should have bid more. Okay. What we refer to as the winner's curse here will, statistically speaking, the difference between the unconditional expectation that I have when I'm making the bid, unconditional on whether I get the object or not, and the conditional expectation that will be informed by me knowing whether I'm being allocated the object, that is whether I'm a winner or not. Okay. Good. Right. So let me just develop this a little bit further. Okay. So suppose you're bidding for a natural resource, such as an oil tract or such as a forest tract that you want to cut trees. You typically will engage in some kind of sampling or some kind of information gathering. And so if test drilling reveals to the driller that the samples are rich, that will probably suggest to him that there will be higher oil reserves and will induce him to bid higher. Okay. Conversely, if indeed that leads me to then win in the object, in the auction, it means that other ones weren't as lucky in their samples, okay? And therefore their samples were not as strong and supportive of a high valuation for that tract. A winning bidder therefore faces adverse selection, that he is selected to get the object precisely when all the others do not find the object as attractive, so the selection is adverse, than he. Okay. And you will notice that the expected value of the tract conditional winning is less than the unconditional expectation. Okay. I'm going to anticipate that in my bidding strategy. So that difference that we refer to as the winner's curse results therefore in bid shedding. Okay, I'm going to place a bit lower than what my expectation is, even in a second price auction, and it will lead to lower revenues. And so the question is there a way that the auction design can attenuate, that is, lower the winner's curse, diminish the winner's curse, in order to improve the revenues? Okay. And to the extent that the auction design can achieve that and can impact the revenue, we want to know whether the selection that's going to be performed by the mechanism will stay adverse. That is, I will only get the object if everybody else thought less of the object, or maybe will become neutral, or maybe even advantaged. Okay. And so today, that is now, we're going to think about what is the revenue maximizing selling mechanism. The interesting aspect of this problem is that there's a long literature, and you will have seen this with Peter, that is in particular related to the beautiful results of Roger Myerson on the optimal auction with private values. And so today we're going to think about common values. Okay, excellent. Okay, and so let me give you in words first the setting that we're going to study, and then of course in terms of a model. Okay, so we're going to think about a pure common value model where once we have collected all of the private information, every bidder values the object the same way. So that means from an efficient point of view, the decision is going to be very simple. We should just give away the object to any one of the bidders. Any one of the bidders or uniform random distribution among the bidders would give us the highest efficient value. Of course, it doesn't tell us anything yet about the revenue that we can achieve. Okay. We're going to allow for private signals that will give the bidder some partial information about the common value. And the key statistical feature, so we're going to speak a little bit about statistics and inference today, is going to be that higher signals will contain more information about the common value than lower signals. So we'll need to make that precise, but in fact, today we're going to make that even starker and going to say that the highest signal, there's the highest signal among all of those that is being realized, is in fact a sufficient statistic for the common value. That is, once I have determined what the highest signal is among all of the n bidders, then I know as much as I can know, and that's going to give me the best estimate about the value of the object. Lower signals, by contrast, carry no additional information. Okay. And just to be sure, we're going to not think about the socially efficient allocation. I said already that that's relatively simple, but rather we're going to think about the revenue maximizing design. Okay, that is what allocation and what prices, what bids will give us the highest revenue. Okay. So now we actually face a serious design problem in the sense that a priori, I have not yet committed myself whether I'm going to run a first price auction, a second price auction, an all pay auction, simply a posted price, whether I'm going to impose participation fees, whether I'm going to impose reserve prices. All of this is on the table. All that I have to do is, of course, satisfy participation and incentive constraint. Okay. To give you an idea where we're heading, we're going to find out that in the setting that we're studying, we're going to get maximal revenue by a very simple mechanism, okay, that when stated at the interim level, so we're going to think about what is it that bidder I knows, but at the moment when he has to decide on his strategy, are going to be a constant price at which I'm going to allocate that object, and there is going to be a constant probability of getting the object. And by constant, I mean it will not depend on the signal the bidder I gets. Okay. Now, I'm saying that just to spur a little bit concern in your mind, okay, because this sounds very different from all that we have seen and heard so far. Right, in a first, second, or ascending auction, in particular with private values, both the price and the allocation is always going to be increasing, therefore dependent on the signal in a particular way, in the value and in the signal. And so you should ask yourself, well, how can that be? And what drives this particular result? Okay. And in fact, I mentioned simple mechanisms. So why do I say simple? Well, if you think about the fact that the price that a bidder who wins pays is independent of a signal, that should remind you of a posted price, right? A posted price is simply a price that I'm going to charge to the bidder, and all I'm asking is the bidder, well, are you willing to pay that price? Okay. And in fact, we'll see that the optimal mechanism in the setting is surprisingly just like a posted price if the probability is such that we always give the object away. So if the probability of getting the object is simply 1 over n, which is the number of the bidders. Okay. It's going to be a little bit, quite a bit more general than that, because often we will see that the probability of allocating the object, that's a typical feature of optimal mechanism, is not going to be 1. That is, I'm going to restrict supply in order to increase the price at which I can sell the object. I'm going to ration, in some sense, the object to allow myself the opportunity or the ability as a seller to not give the object away if the valuation is too low. Okay. Okay. And we will see that there will be necessary and sufficient condition when the optimal mechanism reduces to a posted price, and that is if and only if we're basically willing to allocate the object independent of the signal realization of the bidders. We'll call that inclusive, because we're not excluding any bidder. Okay. In general, though, as we go through the analysis, we'll find that it will be optimal to sometimes include bidder. Okay. In which case, the aggregate probability of assigning the object is less than 1. The interim probability from the point of view of the individual bidder will be less than 1 over n. And now it will be the case that the exposed probability, that is the probability conditional on all of the signals collected, will indeed depend on the entire signal profile. Okay. An interesting feature of this auction is now there is a sense in which we're going to allocate bidders with lower signals. And we're going to discriminate, that's a flip of the side of the coin. We're going to discriminate against bidders with higher signals. And again, this will sound first surprising, but once we follow through the logic of the winner's curse, we will see that there's a good reason for doing that. Okay. And so if I'm now going to translate this statistically, it means that the optimal auction, as opposed to the standard auction, say the first price, the second price, or ascending auction, will induce something that we will call the winner's blessing rather than the winner's curse. Okay, that is, if it indeed favors bidders with lower signal, that means, therefore, that if I'm getting the object, I'm more likely to getting the object with low signals. Therefore, the event of winning actually tells me that there must have been people with higher signals, and therefore I should increase my expectation. Okay. And so we will see that the auction will actually induce advantageous rather than adverse selection. Okay. So this is these were sort of the substantive contribution that we're going to see coming out from the analysis. And methodological, that is perhaps more important for you here, is that what you're going to see is that we're going to derive an optimal auction, that is a revenue maximizing auction, in a setting that is not the private value case, that is the one that you have seen so far, which is really the canonical model for the auction literature. But that a lot of the logic that you have seen already can be extended in very interesting ways to interdependent and common value auctions. Okay. The second new thing that you should see is that before we could rely, when we think about incentive constraint and incentive compatibility, we could rely on, I don't know whether Peter called it the Mealy's trick or not. So I like this expression, is to basically say that the incentive constraint really can be summed up as to just local and adjacent constraints. Here we're going to show that will not be the case anymore once we have interdependent values. Rather, it will be the case that global constraints, okay, and I'm going to formulate that in more detail, are required, and so that will be part of the novel analysis that we're going to offer here. Yeah. Okay. So this should give you sort of a high-level overview of where we're heading. And now I'm ready to jump into the model and do sort of a slow development of the results and guide you towards the central result as we go along.
And just to confirm very quickly, you're absolutely right. I focused on local constraints only. So global is definitely novel, and that's why this is so interesting.
Great, thank you. Okay, so we're in the second lecture, and I repeat my statement, and I'm going to repeat it until I get the first interaction with the audience. I do like to see the video simply to sort of get a little bit sense of your reaction, and I don't mind at all if indeed you ask questions. Okay, but of course you can ask questions also in the chat, and I should add you can also ask questions afterwards by simply sending me an email, maybe CC Emanuele, just that he gets a good sense also of where we should go. And of course, I'd also appreciate feedback, as it has been a while that I've been teaching in Germany. So whether the speed, the content, and the techniques are sufficient, both sufficiently challenging, but also sufficiently familiar that you can follow. Okay, great. So here we come. The model is going to be very simple. Okay, so we're going to think about n bidders that compete for a single object, and the n bidders simply going to receive a signal that's just a number on the real line according to some distribution. So that is our prior distribution, our value, and we're going to say that the true value of the object is simply the maximum of the n independent signals. Okay, that is the maximum signal model. I'm going to refer to this as the maximum signal model. And it's a model that was first introduced in a beautiful paper by Bülow and Klemperer in the early 90s in the Rand Journal of Economics. Okay. Actually, they introduced the model in section 5 of 6 or 7 sections and had just some basic observations, which were very interesting, but they there were many questions that they left open, and so in some sense, we're starting precisely there, and now sort of explore the insights from this model that are actually quite rich to the fullest extent, I think. Okay. Right. So this is the setting. Okay. So the value V, that is what I want to emphasize here. Okay. Does not depend on the identity of the buyer. So it's not indexed. It is simply the highest of all the n signals. Okay. So think about this, basically the one who has the most optimistic sample or the best idea of how to implement, translate the idea or the patent into a marketable product. That's what's going to determine the value of the object. Okay. And so in a way, the distribution of the signals, F, is going to generate the distribution over the common value, V or G of n. Okay. The problem is, of course, that at the moment that we are asking the bidders to make a bid or to submit any information about what their value is, they only know their own signal. They don't know what the signals of the others is. Okay. So while they can form an expectation that will take into account their own signal realization and will form an expectation of the signals of the others, they can't really say what the value of the object is because they just know their own signal, and that gives them a lower bound because the maximum, of course, must be weakly above that. But how far above, they don't know. Okay, so a priori, we have private information, we have some estimate about the value, but we don't know the true value of the object. Of course, bundling all of the signals together would allow us to determine what the value of the object is. Okay? Yes, so this is really a key starting point. We have common values, and the value is simply the maximum of the n independent signals. Okay? Okay. Yes, good. So, good. I want to suggest this has basically two leading interpretations. Okay, I can think about this, and that's how we're going to think about it as a common value model. Okay, higher signal realization contain more information. Okay, and in fact, that was the interpretation that Bülow and Klemperer said, that if if we are trying to drill for mineral rights, the fact that other people have got no positive tests is of no value once somebody found that there is actually some oil under the ground. And so this might be a very good model, statistical model, to think about mineral rights auction. Okay. There's a second interesting interpretation that's sort of relevant for intermediary and dealer markets, where we say, well, we want to think about this basically as a resale market. So the intermediaries are the bidders who are going to get some signal about what the downstream trading opportunities are. And then there is a final sale of the object in a downstream market that's open to all intermediaries. So it's basically, think about this as there is a new company that we can sell. The investment bank basically can make bids that says, I would like to market that company, and here's what I think its value is. That's my initial bid. But of course, the final value is going to be determined by the downstream market. And so you can think about the sample as basically a sample that the intermediary is getting from the downstream market that eventually will determine the value of it. Okay, so then we have now all of a sudden a private value market with resale. Either one of the interpretation will work just fine. Okay. We said in the auction setting, we have to think about constraints. Okay, so the constraints are going to be, as I mentioned before, incentive constraints and participation constraints. So in order to formalize that, let's think about the utility. Okay, the net utility of a bidder is simply the value of the object times the quantity that he gets, or the probability that he gets, minus the price he has to pay. Okay. There's a feasibility of the auction, which simply means that the quantity by which I'm giving it to an individual bidder has to be non-negative, and of course, together it has to be less or equal to 1. Okay. That's about the quantity. I can also then think about the transfer. Okay, there is going to be an exposed transfer that I will have to charge to bidder I. Okay, that depends on all the signals revealed. That is the vector of signals S. Okay, I can also think about the interim, the expected transfer. So that will refer to the notion of interim utility that Peter developed, where Ti as a function of just my own signal is simply what I'm expecting to pay when I know already that my signal is Si, but when I'm forming the expectation over the signals of all the other bidders. Okay. Right. When we're going to think about the direct mechanism. So the revelation principle holds and applies. And if my true signal is Si, okay, but I'm reporting a different signal Si prime, what will I get? Well, there's an allocation probability that now depends on my reported signal, not on my true signal. My value will still depend on my true value, okay? And at the interim level, the payment will depend on my reported payment. And so when we talk about incentive compatibility, we want to think about the situation where truth telling gives me a higher utility than misreporting. That is, if I were to report Si prime when my true signal is Si, and individual rationale or participation constraint is simply the outside option is I'm not getting anything, but I also don't have to pay anything, so it's 0. It must be the case that in expectation, I'm going to be better off participating rather than not participating. Okay. Yes. Okay. So that was the model, okay? Incentive compatibility and individual rationality in the setting. Okay. And now we're going to proceed in 2 steps. I'm going through a set of possible mechanisms, a set of possible pricing mechanisms that will basically increasingly raise more revenues for the seller. So that gets us towards optimal revenue, towards revenue maximization. But that will look at familiar allocation mechanism. And then finally, I'm going to make a claim of how we can raise maximum revenue, and then I can prove that that is the optimal mechanism. Not quite sure whether we can do that on a Friday evening, but we'll try to get there as far as we can. Okay. Okay. And in the process of going through a sequence of mechanisms or pricing schemes, we'll see what role is the winner's curse and how, by basically trying to attenuate, diminish the winner's curse, we are going to slowly increase the revenue of the seller until we reach the maximum. Okay, so it will also allow us to illustrate the winner's curse. Okay, and the best way to do that is really to start with something that we by now are hopefully quite familiar with, which is the second price auction. Okay, it will not be the optimal mechanism, but it gives us a first good understanding of where we're going to go. Okay, so in the second price auction, well, we know what the rules are. So in the maximum signal model, that means simply we want to think a little bit about what's our expectation. Okay, so basically I'm going to be willing to bid as much as my expectation is, okay, given the information that I have. But I will take into account the fact that whenever that bid will be called upon, it's also going to be the case that I'm going to have the highest bid, and so therefore I will have to take into account the winner's curse. Okay, so let's think for the moment just not about the bidding, but simply about the expectations formulation. Then we're going to relate that to the bid. Yes. So I'm going to have, when I'm for my interim expectation, I'm going to know my own signal, and I'm going to use that to form the expectation. So this is this blackboard bold expression here, given about what the true common value is. Okay. The statistical model here is so simple that we immediately notice that my signal is actually a sharp lower bound on what the value of the object is, right? The value is simply the maximum over all the signals, while my signal is just one of these n samples. So the maximum of all samples therefore have to weakly exceed my own sample, okay? And therefore, my signal is a sharp lower bound on what the true value of the signal is, okay? And if I were to just form my interim expectation, then it will always be the case that the expected value of the object that I have, given my signal, will always exceed that signal, because there is a chance that any one of the other remaining n-1 bidders has a higher signal, and that's something that I should take into account when I form the expectation. Okay. My signal is the lowest possible value, but there are possibilities that it might be higher, and therefore my expectation will be higher. Okay, but in fact, in the second price auction, okay, I'm going to simply bid just my signal. Okay, so that seems strange, because in the private value world, I bid in the second price auction the true value of the object. Okay, what we're suggesting here is that I'm not going to bid the true, that is the estimated value of the object that I have given signal as I, but I'm going to bid something substantially less than that. Okay, and why is that the case? Well, it is because I notice that I'm facing the winner's curse. Okay, so the claim is that in a second price auction, I'm going to bid simply my signal. I'm not going to bid my conditional expectation. Okay, right? So I'm bidding, in fact, as if the object is a private value and the value is exactly my signal, not if this is a common value. And the reason is that conditional on winning. Now, suppose I'm winning, okay? Now, all of a sudden, my signal must be the highest signal that's being realized. And now, all of a sudden, my signal that was at the interim level, a sharp lower bound on the expectation of the value, turns into a sharp upper bound, because it's going to be the highest signal, and therefore it's going to determine the value of the object as an equality. Okay. And so in this particular statistical model, we have now a very simple representation of the curse, namely that when bidding, my signal is a sharp lower bound of the expectation of the value, but when winning, it's a sharp upper bound. Okay, and that distinction, that difference in the unconditional expectation, if you wish, unconditional on winning, and the conditional expectation, conditional on winning, is a definition, or is the definition of the winner's curse. Okay, right. So therefore, what I want to say is that different from the private value environment, I'm now not going to bid the expected value, but I'm bidding something less, and I'm bidding simply the signal as I. So because of the winner's curse, there's going to be bid shedding. There's going to be less revenue raised than we would have expected from the analysis in the private value environment. And that bid shedding will lead to lower revenues. It therefore should make us think about, are there ways in which we want to tweak the allocation so that we can minimize the winner's curse and we can maximize the revenue. Okay. Right. So here I'm just saying in words what we already realized in the earlier slides. Okay. Okay. So we want to think about the magnitude of the winner's curse, and we want to attenuate the winner's curse. That's the next. Okay. Actually, let's take a little step in between and think about how can we sort of quantify what the winner's curse is, and can we identify maximum winner's curse with minimal revenue. Okay. And so now we're going to make a conceptual leap a little bit. We're going to think about what's the relationship between the nature of the private information that the bidders have and their bidding behavior. Okay. And to make that leap and to think about the relationship between the private information and the revenue, we basically want to think about what are possible ways in which bidders could have private information for fixed distributional values, and then we want to find the information structure that generates maximum winner's curse. Okay. So how do we do that? Okay. And that will illuminate some properties of the model and the way we go from information to bits and from bits to revenue. Okay. So normally, in particular, if you were to do empirical work, we would start out by saying, well, there must be some fixed distribution of values, of common values among the n bidders. Okay. That is the distribution of values G. Okay. And when we then think about signals and information, we basically say, well, let's think about a conditional distribution, that conditional on the true value of the object, V. The bidders are getting signals. Okay. And these signals are stochastically related, of course, to the value, and therefore they're going to be informative. Okay. To the extent that the signals are the only piece of information that the bidders have when they bid, there's going to be a relationship between the information structure and the revenue for any fixed distribution of values. Okay. And so the maximum signal model that we did today is just an example of a particular information structure, but there are many others, right? And given a particular distribution of values, I can think about partitions, other noisy distributions that I could analyze and distribute, and that's all been done in the literature. Okay. Now notice here, I'm starting out with first a distribution over values, and then go to distribution over signals. In the maximum signal model, the way I presented it to you initially, I started out with the distribution over signals, and then I went to distribution of values. Okay, so here it starts off the dual. And in related work that actually came out, I guess, last year, right? The three of us asked that question, and the answer I'm going to give to you here visually, because that's a much nicer way to represent it. So I'm going to think about a standard auction, okay? So something like a first price auction, okay? But the second price auction would be fine. I'm going to think just about bidders, and I'm going to fix the distribution of values, and it's just going to be a quadratic distribution, okay? It's v squared, okay? And that is the data that I start out with, okay? And then I'm going to think about how does the welfare change, that is, how does the distribution of welfare between bidder and sellers change as I change the information structure. Okay, by information structure, I simply now refer to this conditional distribution that tells me what is the information as the signal that the bidders get as a function of the two values. Okay, I'm going to show you a very simple plot. Okay, the x-axis contains the bidder surplus, maps out the bidder surplus, and the y-axis maps out the revenue. That is what the seller gets, okay? And together, of course, this forms the social surplus, okay? Then what I plot here is the blue line, and that basically tells me what are the possible distributions of the surplus that I can achieve between the seller and the bidders, while I consider the same distribution of values, but just by varying the information. Okay, so the fact that we have a 45-degree line here is what you should expect. Namely, we're going to run a standard auction. We're going to sell the object for sure with probability 1. Therefore, the social surplus should stay constant, and the sum of revenue and bidder surplus should stay the same. It should be on the 45-degree line. Okay, but what's interesting here is that even though the underlying distribution of values is constant, therefore on the 45-degree line, as we change the information structure, as we give the bidders more or less information, we can substantially influence how much surplus they get relative to the revenue that the seller gets. Okay? And I draw a point here that we're coming to, but first I want you to think about the point up here. Okay, what's that point? What kind of information structure could we attain by this point? Well, if, for example, we had complete information, that is, all the bidders were to know exactly what the value of the object is, well, it's common value. That means they're going to compete the surplus all the way up to what the true value of the object is, and it's going to be allocated all in terms of revenue of the seller. So bidders get 0 surplus, seller gets all the surplus under complete information. Imagine there's no private information whatsoever. Well, then what would the bidders do? They would simply form an expectation of the value. In fact, it would be exactly the same expectation that both bidders would form, that would correspond to exactly the expected value of the object. Again, competition would basically mean that the seller in this world of perfect competition would completely eliminate any information or rent for the bidders. And again, we would land up in this point up here where the bidders get 0 surplus and the seller realizes all of the social welfare. So we have a curious result. With either of maximal information, that is complete information, or no information, we're going to get maximum revenue zero bidder surplus. And what I'm drawing you here is that actually as we increase the information rent, okay, or as we increase the value of private information, somewhere in between these two extremes of zero information and full information, there's going to be a point where the information rent is going to be maximized in the standard auction and where the bidders obtain the maximum surplus. The claim that we made in this related paper is that, in fact, this precise information structure that we're studying today, where the value is equal to the maximum of the individually signals, is that the information structure where the bidder surplus in the standard auction is going to be maximized. Okay. So that naturally suggests that in this specific information environment, in this particular common value environment, the information rent is large, the winner's curse is large, and auction design, optimal auction design, has the best chance of tilting the balance again back into the direction of the seller. That is, we're now thinking about basically finding a design that allows us to move into the direction of the seller in terms of the revenue again. And that's a challenge that we have today. Okay. Yeah. Okay. Good. We mentioned that typically we think about local constraints. Okay. Okay. Today, we're going to see that more than local constraints are relevant. And in fact, it will be that all upward deviations are binding. Okay. So here's a question for you. We saw that in the second price auction, bidding the signal is an equilibrium. In fact, bidding more than the signal is also an optimal best response. It doesn't change my value, but it doesn't diminish it either. Okay, and that's because, well, now if I'm going to still win and I have to pay it, it basically is evident that somebody else had a higher signal. So already in the second price auction, global constraints were binding, and now we're going to make them bind also in the optimal auction. Okay, so here's sort of either in the first price or in the second price auction, a simple calculation that says what is the utility that we're getting, then now the bidder's net utility in the first price or in the second price auction. Okay, and of course you see these three curves. Okay, these are the curves for the indirect utility that the bidder of different types can attain in the first price auction, and where you have the vertical line, the black intersection, that's basically the equilibrium strategy and the equilibrium utility. But a surprising picture here is that when I were to move in my reported type to the right, beyond what is the equilibrium strategy, my net utility would neither increase and decrease. And so that's what the upward deviations would look like in the first price or the second price auction. Okay. So we're going to, in the last 10 minutes, think about how we can slowly move into the direction of an optimal auction, and that will be supported by basically thinking about minimizing adverse selection, in fact, moving from adverse selection to neutral selection, and eventually even to advantageous selection. Okay. Right. And phrased in the context of adverse selection, I'm going to say that if you were to stay in the standard auction, where we always assign the object to the highest bidder, then in some sense, that will convey too much information to the winner because it gives him precise information about the adverse selection, namely that everybody else has a less positive view of the world. And that will lead to the winning bet being depressed. Okay. So how about we trying to go for neutral selection? That is, the selection of the winner doesn't tell the winner anything about the signal that the others have. Okay. Now that basically means that the selection must be a random allocation among the bidders. Okay. Because if it were not random, then it would contain some information. Okay. Okay. So, and a specific way to do that is by simply posting a price at which I'm willing to sell the object. And all that I'm then interested in knowing is whether bidders would like to bid or would like to pay the price. Okay, so we're basically going to think about a sequence of posted prices that are going to come very close to the optimal auction, and we're going to halt then at that point. Okay, so here is a very simple posted price that I'm going to suggest to you, and I'm going to call it an inclusive posted price because it will have the property that at that price, the price is just chosen high enough, but at the same time low enough, so that all of the bidders, irrespective of their value, will be willing to buy, irrespective of the signal, will be willing to buy at that price. Okay, how I'm going to compute it? That's a simple formula here. I'm going to set the price in such a way that I'm going to pretend that one bidder, bidder I, has gotten the lowest possible signal. And now he's thinking, well, what is the value if I have gotten the lowest possible signal at all, and I'm still forming the expectation over all of the other bidders? Okay. If I take that to be the price, then that price is low enough that everybody is willing to buy the object at that price if it's offered at that price, because it accounts for the fact that somebody has gotten very negative information, but he still allows for the possibility that others have gotten better. Okay, so I'm going to call this an inclusive posted price because it's set so low that at that point everybody will want to buy, nobody is excluded. Okay, and the surprising result of Bülow and Klemperer in this paper that I mentioned to you, established earlier, is that that simple price, they didn't call it that way, but that price generates a higher revenue than the second price auction. So that price replaces the second price auction, and by absolute, I mean, we are not going to think about reserve prices for a second, and it gives me a higher revenue, okay? Right? So, it's rather surprising. Okay, we're basically thinking about a random allocation now, because since everybody's willing to pay the price, the way to allocate your object is basically give it with equal probability to everybody at that price. The allocation will not depend on the signal, on the private information that the bidders have, and we're not going to select according to either signal value. We're going to maintain the same allocation. Okay. What's an easy proof of this? Are we going to come to that? Well, an easy proof is simply that, right? Look at this price. This price is basically saying I'm going to form an expectation of the value, which is the first order statistic among the remaining n-1 bidders. Okay, because the value is going to be the highest signal, and I'm simply pretending that it's only the other signals that matter. In the ascending auction, or the second price auction, what would be the revenue? Well, it would simply be the second order statistic of n signals. Okay. It turns out that the first order statistic among n-1 signals is higher than the second order statistic among n signals. Okay, and that's a proof. Okay. Okay. Is this the best we can do? Klemperer and Bülow and Klemperer stopped here. They stopped with this result. We're now going to show that we can do better. Okay, and so here's the first way to do better. we're basically now going to say that we're going to allow for the possibility that we are excluding bidders, but we're going to do that not on the basis of the individual signals, but rather on the basis of the value. So we're going to say we're going to give the object uniformly if the highest of the reported signals exceeds a threshold value, and which is R, and if not, then we're simply not going to give it. Okay, and we're basically going to say that we're going to be able to implement that allocation not through an auction, but simply through a pair of prices. Okay. An unconditional price, that is simply a reserve price equal to R, and a conditional price, okay, that's called PC, that's simply forming the expectation over the first order statistic over the remaining signals, provided that the highest of the signals exceed the threshold value R. Okay. Okay. And the point of this is that we're basically saying, would you bidders please tell us what your value is? If one of you has a value that's higher than R, then we're going to allocate it at either a PU or PC at one of these two prices. If neither of you has a value that exceeds R or a signal that exceeds R, then we're simply not going to allocate it. And we're going to give a little bonus if there's only one person that reports a value higher than R. Namely, we're going to then say that person gets the price PU if he gets the object. The other ones have to pay a slightly higher price, that's PC. Okay. And these two simple prices will allow us to actually impose a reserve price, but do that in a way that is uniform, that is conditional on getting the object. I have not learned anything about the winner or the losers or the signals. Okay. Okay, and so here's the first proposition. And this will actually be the last proposition that we're going to talk about too, that shows that this posted price pair can improve on either an inclusive or an exclusive posted price. Okay, and we can actually go one more step further and randomizing the discounted price, and that randomized discounted price will in fact be the optimal price and will be the optimal mechanism, but we don't have to do that today. You should feel free to sort of go through the slides, to the remaining slides, a few, but we stop with this result today that gives you sort of the first indication that once we move from a private value world to an interdependent or common value environment, statistical considerations, in particular those captured by the famous phrase winner's curse, and that's in fact was made popular by the work of Wilson and later on Milgram, come into consideration, and that may lead to substantial rethinking of what an optimal mechanism is, in particular when we think about revenue maximization. Good. It's 1:30, 1:31 in fact here on the East Coast. We have a snowstorm, so winter has started. Let me end here today, unless there are any sort of urgent questions that either from Peter or from Emanuele, and if not, then we're going to resume after a nice weekend on Monday.
Sounds great.
Yeah.
Thank you.
Good. So that's plenty of material for you to think about, but I'll give you the complete references as well over the weekend, and then you should be all good.